Alright, so this video is going to be part 5 of finding the radius and interval of convergence. So we have our power series up on the board that we want to find the radius and interval of convergence of, and that is the sum from n equals 2 to infinity of x plus 3 quantity raised to the n times 3 to the n over natural log of n. Okay, so first off, this is not something that we can make into a geometric or p-series or anything like that that's going to be super easy to solve this with. So we're going to either have to use ratio or root, and since this natural log of n is not raised to the nth power, we're not going to be able to use root test. Okay, so we got to use ratio here, and what ratio tells us, and this is step 1 here, what the ratio test tells us is that we need to figure out the limit as n approaches infinity, the absolute value of a sub n plus 1 over a sub n. Okay, so we do that here. We get, well, plugging in an n plus 1 everywhere we see an n, we get x plus 3 to the n plus 1. That's going to be over 3 to the n plus 1 times natural log of n plus 1. That's going to be all over. Well, we get a x plus 3 to the n over 3 to the n times natural log of n. Okay, that's just our a sub n that is up here. Alright, so now we're going to make this look a little bit nicer by grouping this, and we end up getting x plus 3 to the n plus 1 over x plus 3 to the n. Okay, so our little first grouping right there. Alright, put the x plus 3's together. Next I'm going to put the 3's together, so we get a 3 to the n over 3 to the n plus 1. Lastly, we get a natural log of n over natural log of n plus 1. Okay, so the only thing that you may have trouble with, I mean, you're not going to have trouble with this one or this one trying to figure out what that's going to be, because that's just a little bit of simple exponent stuff. But then the natural log one might take a little bit more thought. Okay, we have the limit as n approaches infinity of natural log of n over natural log of n plus 1. Okay, and what you're going to see here is as n increases, okay, as n increases, this fraction will get closer and closer and closer to 1. Okay, because the value on top and bottom is going to be separated by less and less and less. Okay, it's going to be closer and closer to each other. So what that means is that this is eventually just going to be 1, right? It's approaching 1 as n approaches infinity. Okay, so we don't have to really worry about this. Okay, it's just 1. However, what we do need to worry about here is this x plus 3 to the n plus 1 over x plus 3 to the n, and that will just give us x plus 3, right? The n's go away, and then the n's go away here with the 3 to the n over 3 to the n plus 1, and we're just left with a 3 on the bottom. That's going to be an absolute value of that. Okay, so what ratio test tells us is that this x plus 3 over 3, okay, needs to be less than 1, but it was the absolute value of that, so what we're going to do is get rid of those absolute values and have it be greater than negative 1 as well. So we're going to multiply by 3 on every side here to get negative 3 is less than x plus 3 is less than 3, and we're going to subtract 3 on every side here to get our interval, our starting interval of convergence, which is from negative 6 to 0. Okay, so that's our starting interval of convergence. Okay, so now what we're going to need to do is find the radius of convergence, and really that's just going to take a little bit of number line work. All right, we're starting at negative 6, we're ending at 0, so that means the center is negative 3. Okay, that makes sense because of what I mentioned about power series when I was introducing them, right? That center is x minus a, okay? And since it is x plus 3, the center is going to be minus 3, and that's what this is here. Now from the center to one of these endpoints here, okay, this distance here, I'm done with curly brackets because I suck so much at them, so the distance here is 3. Okay, that's the radius of the interval of convergence, okay? So that means our radius is 3. All right, so now we're going to need to check the endpoints to get our final interval of convergence. So the first endpoint that we're going to be checking here, well, that's going to be this -6. And when we plug that in here, we get -6 plus 3. That's going to be -3. So we have a -3 to the n over 3 to the n times natural log of n. Now we can simplify that, or at least break apart this -3 to the n to simplify it. Okay, so when we do that, we get, well, -1 to the n times 3 to the n over 3 to the n natural log of n. These 3 to the n's go away, and you're left with -1 to the n over natural log of n. All right, and what are we going to do with this? How are we going to prove whether this series is convergent or divergent? Well, we can look at our acronym, right, our checklist that I originally gave you when we're talking about proving series are convergent or divergent. And first, we start with the divergence test, the D. Well, if we did a test for divergence here, we're going to end up with this equaling 0. Okay, we get that infinitely large denominator, and we don't care about this -1 to the n. So divergence test, not going to work. Neither is integral test, comparison, or limit comparison, because we have this -1 to the n here. But alternating series, I think we should have some luck with that. Okay, we need to figure out if b sub n is going to be decreasing, and we need to figure out if the limit as n approaches infinity of b sub n equals 0. Okay, this is our a sub n, so what's our b sub n? B sub n, we need to take out what's making this alternate, which is that -1 to the n. So our b sub n is just -1, sorry, not -1, 1 over natural log of n. Okay, to see if this is decreasing, let's look at the next term in the series by plugging in a n plus 1 for n, and that gives us 1 over natural log of n plus 1. Now, this is going to be greater than this, so that means that the whole fraction, okay, the whole fraction over here is less than the fraction here. So this is indeed decreasing, and that passes the first condition of the alternating series test. Next, we need to determine if this limit as n approaches infinity of b sub n is going to equal 0. And we can see here that we will get an infinitely large denominator, so we're going to end up having this limit equal 0. Okay, and that satisfies the second condition, so we know that this is convergent by the alternating series test. Okay, so convergent. I'll write that right here diagonally. Yep, perfect. So that means that this endpoint is going to be included. Now next, we want to plug in our second endpoint, which is 0. And when we do that, we get a 3 to the n on top, and I have that here. Okay, 3 to the n, so those are going to go away. And then we just have left our, right, I got to write that out first. We have the sum from n equals 2 to infinity of 1 over natural log of n. Okay, looking at our little checklist here, if we did the test for divergence on this, of course we're going to get 0. Integral test, not going to work here. But what about a comparison test? What could we compare 1 over natural log of n to? This is something that we have done before in a previous video. Hopefully you saw that one. But we compare 1 over natural log of n to 1 over n. Right? That's not extremely intuitive, but that's the comparison that you need to make. Now, 1 over natural log of n. Natural log of n is going to be smaller than n, which means that this fraction is going to be bigger than 1 over n. Since the series with 1 over n, the harmonic series, right? Since that diverges, we know that this will diverge by the comparison test. So diverges by the direct comparison test. Okay, the comparison test is also referred to as the direct comparison test. Okay, whereas the L is the limit comparison test. Just a little bit of terminology there. So since this diverges, that means that this endpoint will not be included, okay, because it's not since it doesn't converge, it's not going to be in our interval that converges. Okay, so this is our final answer. All right, so that is going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series, the explanation video for radius and interval of convergence, in the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.